Hi everyone. I will present a paper co-authored by Paul Boniol, Michele Lenardi, Federico Roncallo, and Themis Palpanas. This work is on an unsupervised system for subsequence anomaly detection in large data series. We will first introduce the task and the problem definitions used by the state-of-the-art method for subsequence anomaly detection. We will then point out the shortcomings of these definitions, followed by the description of the approach used in our system, named norm. We will then show you a demonstration of our system and its usage. We will conclude with an experimental analysis comparing the method norm to the current state of the art. Let's first introduce some basic concepts. We name a data series an ordered sequence of real-valued numbers. If the dimension that imposes the ordering of the sequence is time, then we name it a time series. A subsequence of a data series T is a small set of contiguous values of the series T. We define a subsequence using index I, indicating when the subsequence starts, and a length L. The subsequence ends at index I plus L. In this work, we are interested in identifying anomalous subsequences. Note that an anomalous subsequence is not a single value, but rather a sequence of values that can be abnormal, or unusual. This distinction is crucial for the following reason: even if all individual values in a subsequence look normal when examined independently from one another, the sequence of these same values may be anomalous. This means that the trend, or shape of the subsequence may not be normal. We thus define a subsequence anomaly as a rare subsequence of a given length L. An example of such kind of anomaly can be an arrhythmia, or a supraventricular contraction in the electrocardiogram, or an unusual daily electrical consumption. One way to formally define and search for anomalous subsequences would be to use the discord definition. The discord is a subsequence of length L that has the highest distance to its nearest neighbor. In this example, the discord is the red dot, which is defined above, has the biggest distance dj to its nearest neighbor than every other point. The advantage of this definition is its mathematical simplicity. Nevertheless, it has drawbacks. In the specific case of a very large data series in which multiple similar anomalies are present, the discord definition will fail to identify these anomalies. This situation occurs, for example, in an electrocardiogram with several supraventricular contractions. In this first example, the discord, which corresponds to the highest point in the green data series, refers to a normal heartbeat, and is, therefore, a false positive. The second example illustrates the same situation in another electrocardiogram with several similar premature heartbeats, which are anomalous. To fix this issue and detect what we call collective anomalies, the M-discord has been defined as the subsequence with the highest distance to its M nearest neighbor. As an example, the red dots group is detectable using the third discord definition. However, the parameter M is difficult to set. For instance, when the data series is large, similar anomalies might not be correctly identified. To address these issues, a general definition and data structure called the normal model has been proposed. The normal model is defined as a subsequence of length L n M that represents the best the normality of the data series subsequences of length L. In this illustration, the normal model can be seen as a set of subsequences of length L, represented as the dotted circle. We consider anomalous the subsequences that have a large distance to this normal model. A method, called norm, has been proposed to compute the aforementioned data structure. This method operates as follows. For a given data series T, we compute the normal model Nm. We then compute the distance of every subsequence of T to that normal model. The subsequences with the highest distance to that normal model are then considered abnormal. Thus, our system works as follows. The user is asked to upload a data series to the system, as well as the minimum required parameter, which is L. She can also choose non-critical parameters, and also select which subsequence selection variant of norm to use. The system then runs both normal model computation and anomaly detection internally. The resulting score for all subsequences of the given data series is then returned with interactive visualization. Let's now have a look at how the system works in practice. The following sequence is a video of a user screen while using our web application system.
What you are currently looking at is the main frame of the SAD user interface. As we can see, uploading a data series is straightforward. Once the time series is uploaded, an electrocardiogram in this example, the user can optionally add annotations that will indicate where the anomalies are. The annotated anomalies will be highlighted in red. The first action that the user can do is to navigate in the time series. The user can then run our approach, norm, or competing approaches. The user may choose the length of the anomalies to be detected, and the version of norm to execute. When norm finishes execution, it displays the results as a new data series under the original one. This new data series represents the anomaly score. The two time series are synchronized, and the user can navigate through them simultaneously. Then, the user may want to compare the norm results to those of the competitors. For instance, let's take Stomp. The user sets the parameters, executes the algorithm, and waits for the results. The results will be visualized together with the norm results on the same plot. Thus, the comparison is easy to perform. The user may also visualize the internal steps of the norm algorithm. This visualization frame is divided into several steps: subsequence selection, subsequence clustering, cluster scoring, and normal model visualization. All these steps are interactive. For instance, for the first step, the user can change the percentage of subsequences to select. By modifying this internal parameter, which is otherwise automatically set by the algorithm, the results of all the other steps are updated in real time. The user can also choose where to cut the dendrogram, or select the automatic mode based on the minimum description length principle. Finally, in the scoring step, the user can select the cluster to use in order to build the normal model, either the one with the highest score, which is the one automatically chosen by the algorithm, or any other cluster. As we can notice, the cluster that has the highest score is the one that corresponds to the most frequent subsequences, which in this case of the electrocardiogram dataset is a normal heartbeat. Clusters with low scores are mostly composed of anomalies, like in this case, supraventricular contractions.
We can run our experimental analysis using our system on several datasets, both real and synthetic. The real datasets originate from different domains, including medicine and engineering. We notice that the method norm used by our system outperforms the current state-of-the-art methods. This can be confirmed by running a Wilcoxon-signed rank test. This test points out that both variant of norm are statistically significantly better than the other approaches. Regarding execution time, both variants of norm perform well. The variant using random subsequence extraction being up to 1 order of magnitude faster than the competing approaches. To conclude, we address the problem of detecting anomalous subsequences within a long data series, and proposed an interactive system to solve it. This system is based on the norm approach that uses a data structure called the normal model, which represents the normality of a data series. Our system allows users to use our norm method that outperforms both in execution time and accuracy the current state-of-the-art methods for subsequence anomaly detection in large data series. Thank you very much for your attention.